Hello there. You have tuned into the lecture Tree Phenology Analysis with R at the University of Bonn in Germany. Now, as the title suggests, this lecture is about tree phenology analysis with R, but one of the things we'll also be talking about in this class is climate change. Because at least for me, climate change is one of the reasons I'm interested in modeling tree phenology. Because climate change is likely to do something to our trees, to our crops, to all our plants really, and also to the animals, by the way. And it is really through modeling that we can understand what especially future climate change is going to, what effects it's going to cause on our biological systems. So this is why today's lecture will be on climate change, and especially specifically on the drivers of climate change. My name is Eike Lüdeling, and I'm going to take you through this lecture today. The learning goals for today are, we have two learning goals only. We want to understand what drives climate change, and we also want to understand which drivers currently dominate the way our climate behaves. There are quite a few drivers of climate change. Most of us are mostly worried about greenhouse gases these days, but those are not the only driver of climate change. And sometimes people get confused about all these other things that drive the climate. Sometimes people kind of play up the importance of certain drivers that are also important, but are, as we will see, possibly not as important as the greenhouse gases are. But let's go through these drivers, through the important drivers one by one. The sun is a major driver of climate change. Aerosols are a major driver of climate change. Clouds have an effect on our climate. The ozone in the atmosphere and the stratosphere are rather important for our climate. The surface albedo, basically the reflective properties of the Earth's surface, are important. And then we finally have the greenhouse gases. There are some more drivers of climate change that have an effect in kind of the longer term, and I'll briefly mention those, but those are not really the focus of, the lecture today and in general the climate change debate as people lead it today. Now, we'll start with the sun, because the sun is arguably the most important driver of climate on this planet. It warms the Earth through solar radiation, and it does show a bit of variability in the extent to which it warms our planet. So the amount of radiation that reaches us from the sun varies a bit over time. And you can see that illustrated here in these diagrams. The top diagram here shows kind of measured variation in solar radiation reaching the planet. And the middle graph shows a model of the same thing, basically. And what you see is, a bit of variation. It's not all homogeneous. It does go up and down a bit with a cycle of roughly a decade, roughly 10 years or so. And we also see a correlation somewhat to the number of sunspots we observe on the Earth. So sunspots are particularly hot regions of the Earth that somehow look darker to us, but actually indicate sort of eruptions of really dark stuff from the surface of the sun. So whenever the sunspot activity is high, the radiation that reaches us from the sun is a little bit stronger. Now, the differences in the energy that reaches the Earth, however, are relatively small. You see the scale here on the left side of the figure. It ranges from, the minimum is something like, 1358 maybe watts per square meters. And the maximum is something like 1363. So the variation here is pretty minor, and it corresponds to only, about 0.1% up or down compared to the total radiation that reaches the planet. It's not entirely without significance, but it really only explains a very small fraction of the current climate variability that we have observed. The sun is an important driver of climate on geological timescales, but not really a major driving factor of the recent climate changes that we have observed. The second driver of climate change that I want to talk about is aerosols. Aerosols are largely dust. Technically speaking, these are suspensions of liquid, solid, or mixed particles with highly variable chemical composition and size distribution. So it's all kinds of small particles that are in the air, basically. And here's how they affect the climate. If the air was perfectly clean, we would have the situation here shown on the left, where a lot of the radiation from the sun reaches the surface of the Earth, and there's certainly some that is reflected by clouds or possibly by bright surfaces, but basically whatever doesn't touch these clouds reaches the Earth pretty much uninterrupted. Now, if we have polluted air that is full of aerosols, there is an obstacle basically between the sun and the Earth, these small dust particles, aerosol particles that are shown here. These will block a bit of the sunlight from reaching the surface, so it's basically deflected right away before it reaches the Earth. So you can imagine the effect this will have. There are natural sources of aerosols. There's sea salt, there's dust, natural dust, there are volcanic eruptions, there are fires, wildfires that emit lots of dust. But there certainly are also anthropogenic sources. And these largely result from combustion processes, such as power plants, in cars, in fires, man-made fires, and cook stoves. Now, generally, aerosols have a cooling effect on the climate, especially locally. Because if solar radiation is blocked by particles in the air and doesn't reach the surface, then the surface stays cooler. And in some places, these aerosols are major drivers of local climate. Here are two pictures from Shanghai, one on a smog day on the left and on a clear day on the right. And it's probably pretty obvious for everyone that this situation on the left will have a dramatic effect on the weather of this day. You wouldn't expect this to be a particularly warm day, even if above the smog the sun was brightly shining. So quite obviously, this has an effect on the local climate. The distribution of aerosols is not homogeneous in the atmosphere. You can see in this map here the distribution, or it's rather the aerosol optical depth, as it's called, which is an indicator of the amount of aerosols that we have in the air. And you see really bright spots here, red areas, even purple areas in the major industrial centers of the Earth. China is particularly obvious here, but we also have the eastern United States as a large red area here, and also kind of Eastern Europe all the way basically through Russia is also pretty high. Also has pretty high aerosol concentrations, and locally there are some other bright spots, some of which are not really quite visible at this resolution. So this is a major driver of climate in industrial centers, and I'm sure you've all seen these pictures. You just saw one, but you've probably all seen more pictures from China on smog days. Quite obviously, this has a massive effect locally. Clouds also affect the climate, but they can have different effects. They can have a cooling effect and a warming effect. I mean, the most obvious one that we all know from our own experience is that on a sunny day, during the day when the sun shines brightly from the sky, we feel warm. The sun warms the surface effectively. If it's cloudy, that doesn't happen so much. At night, the opposite is true. On a clear night, temperatures go down pretty quickly. On an overcast night, when we have clouds in the sky, the heat is retained and temperatures go down quite a bit less. And here's an illustration of basically what this looks like. It's not all that complicated. We have different types of clouds here. We have cirrus clouds here that are really high, kind of these feathery clouds that I'm sure you've all seen. They usually still allow most of the radiation to pass through and only reflect a little bit. What does happen also, however, is that the water particles here, the water droplets, heat up, and it will eventually release the the stored energy again downwards or upwards in all directions. Clouds can also, as I mentioned, at night, they will block this heat energy that is trying to radiate back into space. Not only at night, but especially at night. We also have these towering cumulus clouds, which are quite a bit at lower altitude, and marine stratocumulus clouds. So basically they have the same effect, but you see here, the lower these clouds are, the more radiation is reflected back into space. But it's relatively complicated what clouds do to the climate. The net effect is likely important. I think most climate scientists agree on that, but it's relatively poorly understood. But there is a chance of a positive feedback loop that could unfold with warming as the planet warms. You could imagine it's sketched up here. If it gets warmer, we get more clouds because there's more evaporation from water bodies and land surface. More clouds may retain more heat on the planet, so it gets warmer, which again leads to more evaporation and more clouds again. It is, of course, also possible that more clouds will, lead to more radiation being reflected and then have a negative feedback effect, which basically cools the planet. So it's not entirely understood how that is going to go. It probably will depend a bit on which altitude these clouds form. As you see in this figure, the lower clouds will reflect more than the higher clouds will. So the next driver I want to mention here is ozone. There are different types of ozone. There's the tropospheric ozone, which is the kind of near-surface ozone, which is a constituent of smog. It's a health hazard. It's not great. It's bad. The bad ozone, you could say. But in terms of climate, what's more interesting probably is the stratospheric ozone, which is quite a lot higher. It's like between 10 and 35 kilometers above the surface. And this is a good thing largely for us because it shields the Earth from UVB radiation, which is quite harmful for life on Earth and including for humans. So this is what we refer to as the good ozone. This is what we want to have. Ozone is, however, also a greenhouse gas. It also has these negative attributes that we associate with greenhouse gases these days. So the presence in the stratosphere of ozone has a warming effect on the planet. Ozone is destroyed by chlorofluorocarbons, so-called CFCs for short. As you've probably all heard, there was the hole in the ozone layer a few decades ago, and probably is still there. Now, the ozone hole is in some way a remarkable story because first of all, it was a huge hazard at the time. It was at least perceived as a huge hazard when it was currently happening. But it also tells an environmental success story that we can learn a lot from. Because as most of you probably won't remember, I vaguely remember, there was a dramatic decline in ozone concentrations, particularly in the southern hemisphere in the 1980s. So here's an illustration of this. On the left side here, you see the southern hemisphere ozone concentrations measured in so-called Dobson units in the 1970s, and here on the right side in the 1990s. And you can see that there's a dramatic decline here. From roughly, like in the center of the hole, from roughly 300 Dobson units to, approximately 100. So that's a pretty massive drop. And it basically signifies, or it causes a lot more UVB radiation to reach the surface and potentially cause damage. Leads to a heightened risk of skin cancer for people, for animals too. And it can cause, various types of environmental damage. This loss of ozone was associated with anthropogenic emissions, same as the kind of climate change we're observing today. These were more specialized, however. Like modern climate change is basically, these are emissions from almost everything we do, but these were emissions from only very specific processes. They were involved in lots of chemical processes like the production of refrigerants, of industrial cleaning solvents, propellants in aerosol spray cans, and also to make styrofoam. This is where these CFCs got released, and lots of them eventually ended up in the stratosphere, destroying the ozone there. In this particular case, humanity got their act together and passed or took decisive policy action. With the Montreal Protocol from 1987, the heads of state of, well, pretty much all countries, but certainly the major production countries, agreed that they would quickly phase out CFCs, and that is actually what largely happened following this agreement. So it is a success story of, well, a problem leading to decisive action, making the problem go away. So the use of harmful compounds has almost completely been stopped, especially in developed countries. The ozone layer has been recovering since 1993. You can see this here, the fairly steep decline in ozone. So this is the percentage change per year. And the anomaly, sorry. This is the percentage change compared to the 1964 to 1980 average. This should actually read ozone anomaly rather than change. But basically, we have this decline here going down, declining by about 5%, and then stabilizing and gradually recovering. The next driver of climate change that I want to mention is surface albedo, which is reflection of radiation by the land surface. This is illustrated here as the solar radiation hits the surface of the Earth. Depending on what it hits down there, it will either be reflected, largely if it hits bright surfaces, or it will get absorbed. If it's reflected, it basically kind of leaves again right away and doesn't really cause a lot of effects on the Earth. If it gets absorbed, however, it will warm the surface, it will warm the soil, or whatever it hits. Light surfaces like ice and snow reflect almost all radiation. 85–90% of the radiation goes directly back out to space. Dark surfaces can reflect very little and absorb most of the radiation that they get hit by. So land cover change can have a serious effect on the albedo, obviously. What you see here is the surface albedo of different land cover types. I've already mentioned fresh snow here, kind of the whitest thing that we find on the planet, and these cumulus clouds can also be nice and white, so they will reflect most of the radiation that's coming in. Old snow will reflect quite a bit less already. Certain types of clouds also are a bit less reflective, and then we get into kind of dry sand here. Reflects still quite a bit of radiation. Wet sand's already less because it's usually darker, and the water will also absorb a lot of the radiation. Dry soil is here. Wet soil, you see, this only reflects about 10% of the radiation that comes in. Water even a bit less. So water will absorb, the vast majority, or like almost all of the radiation that it gets hit by. Forests are also dark, so forests actually also have, of course they do sequester, they store carbon, which is good for fighting climate change, but they also have a very high albedo, or a very low albedo, meaning that they absorb most of the heat that they get hit by. Crops and meadows are also over here, also among the land use types that absorb most of the radiation. Deforestation, you can see from this diagram that deforestation actually raises the albedo. So to some extent, deforestation has a cooling effect. Not saying deforest to fight climate change, that would certainly be a poor recommendation, but it does have this effect on the albedo. Drying also raises the albedo, also has a cooling effect. And what you can easily imagine here is that, once again, there's a potential here for a positive feedback loop with climate change. By the way, a positive feedback loop is not something that is good for us. That's not what positive means here. It is a feedback loop where an effect gets enhanced and accelerated and strengthened. So if you have warming going on, of course, one of the first things that's going to happen, and which we are already seeing, is that the glaciers melt, the sea ice melts. you probably know that the North Pole has been ice-free at times in recent years. And of course, the removal of this really bright white surface there, replacement with water, you can imagine we go from something that is highly reflective to approximately, well, the most absorbing surface that we have. This has an effect. The warming of the planet actually gets accelerated by this process. So the albedo gets lowered, less heat is reflected, and more warming results. In turn, more ice will melt, and the whole cycle might actually kind of spin off into a, well, somewhat very unfortunate spiral. Now let's finally get to greenhouse gases. You've probably been waiting for them to pop up finally. These are atmospheric gases that trap heat on Earth, a major driver of climate change. And here's how this works. You've probably all seen something like this. We have radiation coming from the sun hitting our planet, and then in the atmosphere around the Earth, indicated by this blue halo here, we have greenhouse gases. Greenhouse gases are gases that can absorb only radiation of certain wavelength. They're not great at absorbing shortwave radiation that comes from the sun, so that basically passes this layer of greenhouse gases, but they quite effectively absorb long-wave radiation that comes from Earth. So this is basically the infrared radiation that is emitted by warm ground or warm things on the planet cooling down. This always leads to infrared radiation being emitted towards space, and if they hit these greenhouse gases, they basically stopped. They heat those gas molecules, and the heat gets retained on the planet. So this greenhouse effect warms our planet. Here are some numbers related to this, basically referring to a stationary climate here. We get about 343 watts per square meters from the sun. Some of this is directly reflected back into space by clouds or also by the surface, depending on the albedo. That's where we will lose approximately 103 watts per square meters right away before it reaches the ground. But about 240 watts per square meters pass and actually reach the surface, where about 168 watts are taken up by the Earth's surface and converted into heat energy. This heat energy then causes emissions of long-wave radiation back into the atmosphere, and that basically is supposed to then leave the planet again. So overall, this budget here should be about neutral, even though, of course, in the meantime, some warming of the planet has occurred, which is quite favorable for us, because it raises the Earth's mean temperature from about minus 18 degrees, which it would be without greenhouse gases, to roughly 14 degrees, which is quite a bit nicer for us. If, the Earth was solidly frozen, then we would probably not be particularly happy or even exist. The major greenhouse gases that drive this greenhouse effect are water vapor, CO2, carbon dioxide, methane, CH4, and N2O, nitrous oxide. We don't talk much about water vapor usually because there's very little we can do about it, and for the most part, the effect appears to be relatively neutral. The more troubling drivers of climate change are CO2 and CH4 and N2O, because these have been changing in concentration. They've been increasing in recent years, and that really appears to be driving most of the climate change that we're seeing. So here you see a longer list of greenhouse gases that indicates also the atmospheric lifetime and the so-called global warming potential of each gas. Global warming potential is given relative to the effectiveness of CO2, and it's usually indicated over multiple time scale. In this case, a 20-year time scale, a 100-year time scale, and a 500-year time scale. So CO2 has 1 in each case, and you can see that the other gases are actually quite a bit more potent. They have a lot more global warming potential, partly because some of them are retained in the atmosphere for a very long time. This one here, for example, tetrafluoromethane, it's estimated that the residence time of a CF4 molecule in the atmosphere is about 50,000 years. That's a long time. For carbon dioxide, this was only about 30 to 95, still quite a long time. Now, we might think, of course, when we see these numbers that, oh, well, if we want to fight climate change, we should predominantly focus on the gases down here because they have much higher numbers than the other ones up there, which is not a wrong idea, but we also have to know that these gases here are only in the atmosphere at very low concentrations. They're all anthropogenic. They all are produced by some sort of chemical processes that humans have invented, but they're really not quantitatively all that important as the other three up here. And here we have, nitrous oxides here, methane, both of which are quite strongly related actually to agriculture. And then we have carbon dioxide. This only has one here, but because quantitatively we have so much more carbon dioxide in the atmosphere than all the other gases, this is actually the major driver of climate change, of the climate change we're seeing today. A few words about longer-term drivers of climate change. There are actually trends in solar activity over time. These are not the sunspot cycles, but they're related to the star life cycle. So basically, stars go through certain developments as they hang out in space for the billions of years of their lifetime. So also our star is gradually decreasing luminosity, experiencing decreasing luminosity over billions of years. This is something that has, since our planet is a few billion years old already, this has certainly left a mark, but it's not really closely related to the climate change we're seeing now. Similarly, for ocean currents or the continent constellations, I'm sure you all know about plate tectonics, and you know that the continents weren't always in the places where they are now. Here, for example, is an illustration of what we believe the Earth to have looked like in the late Cretaceous, so when the dinosaurs roamed the planet. There's some marked differences here compared to what we have now. All the light blue and the purple areas here are seas and oceans, and you see that there are some rather significant differences here in how the water circulates on the planet. Large-scale water circulation is basically transfers heat from one world region to another. In this case, we see here, for example, the so-called Isthmus of Panama was open. North America and South America were not connected, and so the warm water could escape here, could basically flow out. It was not forced, as it is now, to flow up the coast of America here and end up in Europe. So the Gulf Stream, as we know it, didn't exist at the time. There's some warm water reaching Europe here too, but it's certainly not as significant. It wasn't as significant as it is now. Same with Antarctica down here. Also a remarkable difference is that you can't really see that here, but Antarctica is still connected to Australia, and Australia stretches pretty far north. So Antarctica is not isolated here. It is not surrounded as it is today by a circular, really, really cold current. So only when that cold current formed is really when Antarctica started freezing over. As the continents shifted, the ocean circulation patterns, got adjusted accordingly, and that had some major effects on the global climate. Again, not something that you can really watch happening in real life, so this is also not closely related to the climate change we're seeing now. There's a slightly hypothetical story about plants versus animals way back in the past, hundreds of millions of years ago, which basically is a story about the balance of CO2 production and consumption. When you know that animals largely take up oxygen, breathe out CO2, and plants do the opposite. And now a stable climate sort of relies on these two processes being in balance. So you want about as much CO2 to be consumed as is emitted. If CO2 accumulates, you get strong heating, and if it gets depleted, the Earth warms. the Earth cools. And there was a fairly interesting period back in the past, like I think 750 million years ago or something, of a period of so-called snowball Earth and greenhouse Earth. So basically a few times there was a flip back and forth between a planet that was basically frozen solid, and a situation directly after and before it where you had coral reefs growing in all kind, basically it's what seems like the whole planet basically. So very warm, balmy conditions, and then again flipping back to the snowball state. So it's quite possible that this balance between the organisms hadn't quite established at that time. There's also volcanic and meteorite activity. Volcanoes emit CO2, having a warming effect, and they emit dust, which has a cooling effect. And there have been several eruptions of supervolcanoes in the past in different places on Earth that caused massive effects on the planet. Especially in some cases there were dust clouds also by meteorite impacts that persist for several years and then create all kinds of effects that then again have kind of follow-on ripple effects that kind of affect basically the whole planet. Yeah, if basically the sun gets blocked out for several years, you can imagine the kind of effect it will have on plant and animal life. A fairly interesting phenomenon that we also see driving our climate is the so-called Milankovitch cycles, which basically describes variation in the Earth's orbit. And these are the eccentricity, the axial tilt, and the precession. So the eccentricity basically means how elongated the Earth's orbit is. Yeah, because at some point, like this is a cycle that goes over several thousand years. At some points in this cycle, the Earth reaches a point that's further away from the sun than at other times. It's never quite as circular as it's shown here, but this certainly varies quite a bit. And you can imagine that this has an influence on the climate, because it basically determines how cold it can get during the cold season. And then there are two states of our planet that are related to the axis of the Earth. First of all, there's the obliquity, which is basically the tilt angle here, which isn't always the same. Yeah, so at the moment it's something like 23 degrees or so, but it has actually varied over the millennia between about 22.5 to 24.5, and that again determines which hemisphere gets hit by how much radiation at what seasons, and that also has had quite an effect on our climate, partly because the land masses are so unevenly distributed at the moment. The last effect then is related also to the axis of the Earth, not to the tilt so much, but to the fact that it kind of wobbles around a bit. So the tilt remains the same, but basically the axis describes kind of a circular movement here. It's called precession, and that is also something that experiences a certain cycle and has an influence on the climate. This is the most likely cause of the ice ages, by the way, these Milankovitch cycles. Here you can see how this the illustration of how this appears to have developed. So here's the first of all the cycle related to the precession. You see this has a fairly high frequency, but it shows a lot of ups and downs. This is the axial tilt, so the inclination of the Earth axis. This also shows quite a bit of variation. And then this is the longer-term cycle related to the Earth's eccentricity, so how elongated the orbit is. And from this we can calculate the solar radiation that hits the surface of the Earth. In this case, it's at 68 degrees north in summer. Yeah, so this, of course, this varies a lot depending on where you are on the planet. And it's also been quite closely related. We've been able to relate this variation here to the ice ages. So this is basically describes the temperatures as they've been estimated, variation between cold, which is always ice ages, or basically everything except these peaks here is basically ice ages, and then the hot period, the warm ages here are up here. So again, the most likely cause of ice ages is these cyclical movements of our planet. So we've seen that many factors influence the climate. Sun, aerosols, volcanic eruptions, and ozone, and greenhouse gases, of course, are probably the ones that are most relevant for us today. And fortunately, we can quantify the influence of all these factors because we have pretty skillful climate scientists who have figured out a lot about how the climate system works. There are models, there have been lots and lots of studies, and we understand quite well the impact that all these different factors have, to the point where we can make attribution studies. So here you see a climate change attribution diagram, and what's shown by the black line here is the temperature, the global temperature that's been observed basically since the early 20th century. In this case, the graph ends relatively early. Of course, when we could draw a longer one now. And this shaded area here, the brown line and the gray shade around it, indicates predictions by different models. So basically, we're trying to reconstruct the climate, the temperature change that we've observed with models. You see, it doesn't totally overlap. That's often the case because the climate is pretty complicated. We have a big planet and we don't fully understand everything that happened. And of course, there are also kind of gaps in data when we go back into the past. But we can attribute these changes basically to changes in these different drivers of climate change. These are the colorful lines here at the bottom. And for each of them, we can estimate the contribution to the temperature change. So the model forcing response. And well, the most striking one maybe, or let's say the one that maybe wouldn't expect so much, is this cooling effect here. These sulfates is basically the aerosols, the dust particles, have had quite a significant cooling effect probably. So we're estimating that here in the late 90s, this was probably a cooling effect of about 0.3 degrees below what the climate would have been without these aerosols. Same with volcanic eruptions. I mean, it's gone up and down quite a bit, but lately here, there were a few volcanic eruptions here. Mount Pinatubo is one of them that, well, as far as we understand the climate, also had a cooling effect. Now, these get overcompensated, however, first of all, a bit by ozone, by variation in the solar radiation. That does have a small effect, as you can see here, or not that small. 0.2 degrees is not all that small, actually. But we can really only understand the overall temperature dynamics that we're seeing if we add greenhouse gases to the equation. The estimated effect here already by the late 90s was 0.7 degrees of additional temperature increase. So without human influence, these observations that we are making can't be explained. Greenhouse gases are the primary culprits for recent warming. That is, I would say that science is actually rather settled by now. And it's not very surprising because we've seen a strong increase since the onset of industrialization in CO2, methane, and nitrous oxides in particular. Some of this is already measurement, so we can now, of course, measure directly the concentration in the atmosphere of these various gases. That's the line here. But then we also have all these dots. Dots allow us to go back in the past, and basically these dots indicate samples of the atmosphere, of the historic atmosphere, that we derive from ice cores. So small bubbles of air are enclosed in ice cores, and we can analyze the concentration of those. And this gives us a fairly good idea of how the concentrations developed back in the past before we had real measurements. And we see that for all three gases here, for CO2, for methane, and also for nitrous oxides, the past 150 years or so have, well, been the period when these started increasing. And this is, well, a development that went in parallel with the Industrial Revolution and the type of industrial society we live in today. The source is really obvious. It's human activity, and it's in particular the burning of fossil fuels. Now, where do these emissions come from? We know it pretty well. It's an easy accounting game. Of course, there's lots of accounting, but we have that figured out quite well. Some emissions come from forestry and other land uses. That's the brown area down here. But most of these emissions come from fossil fuels, cement, flaring. Flaring basically means the burning of gas that gets emitted on oil fields. That's also this is the main driver: burning fossil fuels and making cement. So the human emissions currently are on the order of something like 40 gigatons, 40 billion tons of CO2 equivalent per year. This is the same figure here, or the same numbers basically. But with some additional detail, we can see where these emissions come from. We see the European Union here is a major contributor. United States, China is the biggest factor now, partly because they produce all kinds of stuff for the rest of the world right now, and then the other regions are also there. But I don't really want us to highlight, to focus on these different countries. The scary part is really the way this curve has been going up and still is largely going up. I mean, there's been some improvements recently because some people have started taking this issue really seriously, and that's gratifying to see. But overall, we're still at or near peak emissions, the highest emissions we've ever seen. So in this figure here in 2018, it was about 37.1 billion tons. It's probably, on the order of about 40 billion now. And despite regional progress, we're still seeing this dramatic increase here, and it's a pretty frightening situation. It's frightening because we're entering new climatic territory here. The atmospheric CO2 concentrations are already higher than they've ever been before since the origin of humanity. Humans have never experienced higher CO2 concentrations. You can see that here, this graph here is also largely derived from ice cores again, shows the CO2 concentrations in blue here since about 450,000 years ago. And you see there's all these ups and downs here, largely related to ice ages and warm ages. And then all of a sudden, industrialized man enters the scene, and these emissions, or these concentrations, skyrocket to levels that are absolutely unprecedented and on this time scale. They've not only never been so high, they've also never been rising so fast. Possibly never ever in the history of our planet. That's a little bit hard to tell, but certainly not in the human experience. What we're not so sure on, because it hasn't happened so far, is what the effects on temperature will be. What we do know, however, is that in the past, temperatures, global temperatures, local temperatures in many places have been closely correlated to these CO2 concentrations. You see the peaks here largely overlap. And so that is why we are actually, like, no serious climate scientist is surprised that given these increases in CO2 concentrations, we're also seeing a simultaneous, fairly dramatic rise in global temperatures. Now here are my take-home messages. The drivers of climate change are many factors. There are many drivers of climate change, but most of them operate over very long time scales. Most of them also don't vary that much. Most of them are kind of there, go up and down a little bit, but don't actually have a very strong influence on our day-to-day weather, certainly, but also climate over several decades. Recent warming can only be explained by rising concentrations of atmospheric greenhouse gases. So that's what I wanted to say, what I wanted to tell you today. The next lecture that's coming up will still be on climate change, and it will deal with recent warming that we've already seen over the past decades. Thank you for your attention.